Military radar networks across the Western Pacific are facing an unprecedented reality as China officially transitions its newest fifth-generation fighter into mass production. This is the Shenyang J-35A, a stealth fighter, a platform that was once written off by international observers as a flawed clone of the American F-35. 14 years ago, in October 2012, its early prototype, known as the FC-31 Gfalcon, made a smoke-heavy debut at the Zhuhai Air Show, prompting many global defense analysts to argue that the project was a failure after being rejected by the Chinese Air Force. The program was left financially vulnerable and exposed, seemingly with no tactical salvation. Fast forward to mid-2026, and the tables have turned completely. Recent satellite imagery and factory flight tests at the Shenyang Aircraft Corporation facility confirm that this once-abandoned airframe has evolved into a highly optimized, dual-engine stealth weapon that is now rolling off assembly lines in serial numbers. This massive industrial pivot leaves regional defensive strategies suddenly feeling defenseless against a saturation wave of low radar cross-section threats. How did a platform that was once considered dead and useless reinvent itself to challenge global aerospace dominance? And what secret engineering allowed Beijing to leap from prototype to mass production so quickly? We are going straight into the cold, hard data. Before we go on, do you think this massive production push will permanently tilt the balance of power? Let me know your thoughts below. Hit that subscribe button for more deep defense analysis, and tell me where you are watching from. The secret behind this rapid industrial acceleration lies deep within a massive factory expansion, verified by global defense analysts analyzing commercial satellite imagery. Leading aerospace researchers have identified over 8 million square feet of newly constructed assembly workshops at the Shenyang facilities. To bypass the traditional, slow manufacturing processes that slow down Western supply chains, engineers utilized advanced 3D laser printing technology to manufacture massive, single-piece titanium alloy structural components for the aircraft fuselage. This engineering breakthrough eliminated over 50% of the traditional mechanical fasteners and rivets required for assembly, radically increasing structural strength during high-gravity air maneuvers, while accelerating factory output toward a projected rate of over 100 aircraft per year. At the core of this mechanical chassis is a dual-engine configuration that marks a sharp departure from the single-engine design of the American F-35. The newest production models are powered by two WSnineteen Huangshan turbofan engines, replacing the older WS-13 E test engines. These next-generation powerplants deliver a combined maximum thrust of 200 kilonewtons under full afterburner. This dual propulsion setup allows the fighter to achieve a maximum speed of Mach 1.8 and grants it supercruise capability, enabling it to maintain supersonic flight speeds without engaging fuel-heavy afterburners. On paper, this mechanical design provides superior kinetic acceleration and a higher safety margin during extended operations over the open ocean. By pouring billions of US dollars into automated assembly lines and specialized component forging, the industrial strategy has focused heavily on reducing the flyaway cost to an estimated 55 million to 70 million US dollars per unit. This low-cost strategy enables a sheer volume of advanced aircraft that can test the capacity of any sophisticated defensive network in the region. To truly understand the operational deployment of this mass production fighter, defense analysts emphasize distinguishing between its specific variants. The model entering mass production for the land-based Air Force is specifically designated as the J-35A. This differs significantly from the naval carrier variant known simply as the J-35. A close examination of the landing gear of the J-35 reveals a single-wheel nose gear configuration with a more streamlined design. This design feature reduces the empty weight of the aircraft compared to the naval variant, which requires a heavy twin-wheel nose gear and a dedicated catapult launch bar to survive the electromagnetic aircraft launch system of the Type 003 Fujian aircraft carrier. By eliminating the structural weight of the naval arrestor hook and folding wing mechanisms, the land-based J-35 optimizes its fuel capacity to achieve an unrefueled combat radius of 1,200 kilometers. Internal weapon bays hidden inside the fuselage allow the aircraft to carry 4 PLfifteen E long-range air-to-air missiles. These missiles feature active radar homing and possess a maximum engagement range of 145 kilometers, allowing the fighter to execute beyond visual range engagements while maintaining its low radar cross-section profile. The primary tactical objective of the J-35 is not global power projection, but rather operating as a high-volume, forward-deployed interceptor network close to its home territory. While the Western F-35 is designed as a multi-role strike fighter, the J-35 is built to saturate regional airspace, providing a dense stealth screen that challenges opposing surveillance networks and leaves older fourth-generation assets exposed and vulnerable during high-intensity aerial confrontations. Despite the rapid industrial momentum observed in mid-2026, leading global defense analysts argue that the J-35 faces a critical manufacturing bottleneck that could slow its actual combat readiness. While the automated assembly lines can manufacture the airframe at high speeds using advanced 3D printing, the mass production of its propulsion system remains a complex challenge. The primary risk over the next 12 months involves the production rate of the newest WSnineteen Huangshan engines. Forging single crystal turbine blades capable of enduring high operational temperatures requires extreme precision. If engine production cannot match airframe output, early production models may face operational delays or be forced to utilize older WS-13 E engines, a compromise that would reduce the overall stealth and supercruise efficiency of the fighter. Furthermore, maintaining the advanced radar-absorbent material coatings in the high humidity and high salinity environment of the Western Pacific represents a long-term logistical burden that will test the maintenance infrastructure of the Air Force. The strategic lesson of the J-35A program is that modern military modernization is no longer just a competition of individual technological perfection, but rather a war of industrial mathematics and attrition. By intentionally optimizing a low-cost, highly capable fifth-generation platform, the strategy shifts toward overwhelming sophisticated defensive networks through sheer mass, forcing opposing defense planners to account for hundreds of low-radar cross-section threats concentrated within a single region, fundamentally alters the cost equation of modern air defense. The arrival of mass-produced stealth assets alters regional dynamics, turning what was once a theoretical balance of power into a highly contested reality. Will this high-volume stealth strategy prove more effective in a prolonged confrontation than relying on a smaller number of highly advanced, expensive aircraft?